Hi everyone, my name is Huangshi, and today I'm going to present CrystalPerf, an approach to characterize the performance of Dataflow computation. Nowadays, Dataflow computation has been underlying many lucrative businesses and cutting-edge technologies. For instance, big data analytics can process a large number of business records and generate valuable insights and facilitate business decisions. In the Internet of Things, the streaming frameworks can process quickly arriving data and coordinate a large number of networked devices. In health industry, the artificial intelligence has provided us with more efficient and economic ways of diagnosing diseases. Across all those scenarios, Dataflow computation has been the key enabler behind all the innovation and growth. However, given such diverse environments and different workloads, it's very challenging for those frameworks to provide a convenient tools for development and deliver a smooth deployment experience. Now let's have a look at how it'd be like to develop with Dataflow frameworks in a real world. Here is the story of a data analyst, Jane. She is developing a machine learning model for her medical project in TensorFlow. And after finishing the program, she finds the scalability of her program cannot live up to her expectation. As she collects more and more data, the training time grows exponentially despite the multiple GPUs in her machines. So she gets very confused about the behavior of this program and why all those GPUs cannot work properly together. To solve those problems, Jane first attempts to visualize the model with a built-in tool. The graph is very detailed, but it's a static graph, so Jane still cannot know which part of the program has taken most of the time. In view of this situation, she switches to a dynamic profiler, also provided by the TensorFlow. It can collect the runtime events during the execution, but its problem is that it gives too much low-level information. For instance, it consists of over 3,000 operators and over 9,000 of tensors. Those low-level information can easily drown out the real cause of the problem. Therefore, Jane still cannot figure out why her program cannot scale well. To summarize, despite the glorious development of Dataflow computation, S2 chain is still far lagging behind in terms of convenience and practicality. To improve the status quo, we have collected the common problems from those Dataflow developers, and we find most of them are actually results-related. For instance, if they find the deployed applications run much slower than they would expect, they have to debug the performance of those applications. And furthermore, if they want to accelerate it, they may wonder what resource can bring in the most performance boost. Finally, if they want to optimize the program itself, it typically starts with the question, what resource is the bottleneck? To summarize, they want to characterize the performance of those Dataflow applications in terms of the resources. And we have some existing solutions in academia, but we find most of them are either framework-specific or intrusive to the systems. So the objective of this work is to find an approach to performance characterization that is general to most of the Dataflow frameworks and convenient to use without the need of instrumentation. Here is an overview of our approach. Given a Dataflow job, we need to establish a relationship between the time and the resources. So on the time dimension, we can attach a sampling profiler to the process of those tasks. And the profiler will periodically sample the call stacks during the execution. From that result, we can know what functions are being called at each time point. And then we need to correlate those functions with the resource usage. And here comes our contribution. We have designed two machine learning models that can infer the resource usage from the source code. We choose source code as the analysis target because most of the functions are from the open source Dataflow frameworks. So we can access the source code of those functions. And our model can infer what resource is the dominant resource of the source code and assign a label to those functions. With all those labels, we can aggregate them and get a resource time breakdown. This essentially says how much time has been spent on each type of resources in each task. And this will be a key piece of information for our analysis. In short, our approach has two advantages. First, it collects runtime information with a non-intrusive sampling profiler. And second, it only exploits resource information from the source code without resorting to the framework-specific semantics. So that's how our approach can be both instrumentation-free and framework-independent. The rest of the presentation is organized as follows. I'll first introduce how we design our classifiers and how we assemble those classification results into an execution profile and debug the performance. Then we extend our approach with some resource models so that it can predict the job performance under different resource configurations. First is the classifier, which is the core of our work. As I've briefly introduced, the classifier can predict the resource usage of a snippet of code. So the input of our classifier is the source code, and now we have to define the output of this classifier, which is we have to formulate the resource usage into a mathematical form. And we choose to do it with a resource vector, with each component representing the probability of a snippet of code using a certain type of resources. So as an example, on this figure, the 0.73 means this function has a probability of 0.73 of using CPU as its dominant resources. And currently, the resource vector has 3 fields, but it is extensible to other new resources. And we have designed 2 separate models for the code and the documentation separately. So they have a similar structure. Both of them have 2 phases. The final neural networks are the last phase, and before that is the embedding phase. So in the embedding step, we convert code and the documentation into a vector. So for more details, you can refer to our paper. Now that we have designed 2 classifiers, we have to train them with some labeled dataset. Since that there is no standard datasets in this respect, we have manually collected them from some large open source projects. And there are around 5,000 functions in total. And those labeled datasets is used to train those classifiers. We need to make sure that they have learned meaningful patterns instead of just some noisy information. To achieve this goal, we resort to an explanatory framework called LIME. It's a machine learning framework that can explain why a model makes certain predictions. And here we assemble the top 5 words that make those classifiers predict a certain type of resource. And the results conform with our expectation. For example, the key computation is a CPU-dominant function. The file operations may be bound by the disk, and also the socket represents a network operation. So this means our classifiers have learned meaningful models from the source code, and we can safely use them in our analysis. With those classifiers, we can apply them to the call traces of each operator and derive the resource vector of each operator. And from the framework logs, we can get the runtime of each operator. With those 2 pieces of information, we can approximately estimate how much time has been spent on each type of resources for each operator. For instance, for the operator sigma, we can multiply its runtime 25 with the CPU entry in the resource vector and get the CPU time of this one. By adding up all those resource time, we can see most of the time in this Dataflow job is spent on CPU, and we can say that it is bottlenecked on the CPU. With those information, the developers can optimize in this regard accordingly. Furthermore, we designed 3 resource models to enable the prediction of job performance. Those models essentially answer the question how a runtime would change given a resource variation. So as an example, on the right side, we show the prediction of a job runtime under the circumstance of doubled CPU share. In that situation, our model predicts that operator sigma will run faster by 7.5 seconds, and it predicts similarly for all other operators. And by aggregating all those predicted runtime, we can get an overall runtime for this job. So for the details of those resource models, please refer to our paper for more information. The performance prediction and the performance analysis have both been implemented as a CLI tool. It takes the framework logs and the sampling traces, and it outputs the performance diagnose and the performance prediction. We have evaluated CrystalPerf in terms of the prediction accuracy. For this, we have collected 6 different workloads across 3 popular Dataflow frameworks. So first, we run each workload under its default configuration, and then we vary a single type of resources. To know how good the prediction is, we run the workload under that configuration and obtain the actual runtime. So as an example, the 2 figures below show the workloads in TensorFlow framework, and each bar group refers to one variation in resource. And as we can see, in general, the CrystalPerf can predict the performance within a deviation of around 14%, which is sufficiently accurate as a developer tool. Also, we apply CrystalPerf back to Jane's pool scalability case. So by reproducing her case in the exactly same cluster environment, CrystalPerf takes in the runtime log and identifies the bottleneck as I/O. So with that information, we enable NCCL and optimize library for I/O as a remedy, and we find the scalability significantly improved. We have more evaluation results in our paper that showcases the robustness of our approach against labeling inaccuracy and its generalizability to other frameworks. To conclude, we have proposed CrystalPerf, an approach to performance characterization for Dataflow frameworks that is framework independent and instrumentation free. So that's all of my presentation. Thank you for listening.